derivative feedback, that kind of things. We were seeing what is the advantage of each one, and eventually we saw that if we combine all of them, we can get a versatile controller, like we called it PID. Means we can have all type of the proportional feedback, derivative feedback, or integrated feedback. And then at that time, we were saying that these things may improve stability or uh, decrease the stability or increase the speed. We got some sense from each of type, but we haven't really studied the stability in the quantitative way. And then the next part of this course, we try to uh, show several tools or calculation tools that helps us to figure out whether the system will be unstable when we are closing the loop. So uh, the first way or first technique that we used called router widths. Yeah. Oh, okay, okay. Let me change it. Yes. Okay. So the first technique that we used was I want to okay, right. The first technique we used was router widths, which starts with a closed loop polynomial, and we try to understand whether this given polynomial is, which is the roots of the closed loop system, is stable or not. And it has some sort of technique. We just give a small example here for just reviewing. So the way was we just try to write the coefficient of this s in the polynomial in a specific order. We put this 3 here, this one here, this 3 here, right? This one here, this here, and so on, right? In this format. And then we try to calculate something like the determinant of the 2 by 2 matrix. For example, the first matrix is like this. So the determinant we calculate is 1 times 3 is a negative of the normal determinant. 1 times 3 minus 1 times 3 will be 0. We put it here. And then the next matrix is the next matrix will be where? Okay. Between this row, this column, and this column. And then if you calculate again, will be 0 here. So this is one special case that you will see that whole row is 0. And then this special case, we mentioned that when we reach that region, basically we need to use an auxiliary equation to further go on. And then the auxiliary equation in that case is we use the previous row to write it. And then again, we write the basically up to here. And then we write the auxiliary equation like this. And this S4 is coming from this row because this row was for S4. And then each coefficient is belongs to like this. This one is for this. The same order that we put it from the top equation, basically. The second one is this one, and the last is S4. And then we take a derivation of this equation, the auxiliary equation, and gives us next level. And this next level, actually, we should put the coefficient from this next level instead of the 0 and 0. So let me clean it a bit and then continue. Okay, so now we reach to this auxiliary equation on top and then take a derivation and we come up with this. And here we put this 2 over here and this 4 to here instead of the 2, 0. And then we will continue, right? Again, to continue to the next level, here is the matrix. What is the calculation of the determinant of this? Is 2 times 1, right? 2 times 1 minus 1 times 4. Divide by 2. So the next row would be, call it as 2 times 1 minus 4 times 1, and then divide by this 2, right? And since there is no other column over here, actually there is. And then the next one is basically 2 times this one minus 1 times 0. Divide by 2 will be 1, right? And this will be negative 1. And there is still one level more. We can continue to calculate this element here, right? But I don't continue because I am already seeing that there is one sign change. When you look at the first column, was positive, then positive, then positive, but here become negative. And this sign change means that the system is not stable, right? So if our goal is just understanding whether the system is stable or not, this sign change already saying that this is not stable, right? So we can keep continuing, but this is not necessary now. And then there was another way to find the stability of the system. We called it root-Lucas technique, which we try to find where the position of the closed loop poles are. So this, we gave a simple example where the open loop system was just like this, S plus 1, I guess, right? Yeah. The open loop was like this, and the closed loop we could calculate and reach to this value for the closed loop poles when we are varying the parameter k. And then if you vary the k, this is just based on the simple calculation of the second order system. You will see that the poles of the closed loop starts from the original open loop in this plane, and then it moves once you increase the k to this side, and then they intercept each other, and then they will again go out to infinity. So we can know how the poles of the closed loop changed versus the k, which the k is, let's say, our tool to control the whole loop. So for the small systems, it is possible you derive this by like fully calculate, put it inside the closed loop and fully calculate the roots. But for more complex system, it's difficult to really understand how this equation is going to work. And then we are giving some techniques to solve this for more complex systems. So since we can know the location of the roots, then we can estimate how is the stability of the system. how the speed is and if there is any oscillation or if there is any overshoot, right? So let's say we start from the open loop. We know the loops are at these two initial locations, right? If this is open loop, we know that the system is marginally stable because there is one pole at the origin. But once we increase the K, we know that the poles are coming to this real region and then they intersect and then they separate. And this, when they are separating, we know that this kind of like second order system with some damping factors and some overshoots. I mean, we already have some sense of how the response is, right? So let's see how we can systematically try to find the root locations. So first of all, we have the open loop transfer function. So the open loop transfer function, we can write it like this. We separate all the poles and zeros of the open loop transfer function first, right? And then what we try to solve is, in fact, first of all, we know when there is no k is equal to 0 means the loop is open, basically, right? The poles of the system is basically at this the open loop origin, the same as the open loop. And then what else we know from these equations is that when k becomes too big or go to infinity, then the poles start to moving through to the zeros of the system, right? We have mentioned that we have some poles and some zeros, right? When the k is 0 means we don't have any feedback basically, and then the system is open loop basically, and then the poles are basically these poles, the open loop poles. But in the feedback, when you increase the k to the infinity, then these poles start moving to go to the zeros of the transfer function. And in case we don't have any zeros, then they need to go to infinity. So we give the example and you can understand how it is. So let's try to, let's say, find the root locus for the closed loop system for this system. So this system, let's say, has 3 poles, right? This system is a 3-pole system. We start putting them on the S-plane. So there is a pole at 0, one pole is at -1, one pole is at -5. So how is the stability performance of the open loop? This is just marginally stable because we have one pole at this origin, which is just at the center of the S-plane, right? If goes to the right, it will be unstable. So we want to know where the closed loop, closed loop roots can go. So there is a technique. First of all, we try to find the location that on the real part, of the S. We want to know in the real part of the S, which locations are possible to be the root locus. So for that case, there is a simple rule. So on the real side, you should always have an odd number of poles or zeros on your right hand to become a root locus, right? So for example, can this side of the S plane on the real, can this side be a location for the roots? So is there any odd number of roots or zeros right hand side of this? Right? There is no. Right? Since there is no, then this region cannot be the root locus. Right? Roots of the closed loop cannot be at this region, at least we know for the real. Then how about this section? How about this section? It can. Why? Because we have one pole, odd number, right? And how about this section? Is this section possible to be location for the roots? Cannot, since we have even number of the poles, right? And then the last section also can be, right? Because we have three poles at the right side. So basically, from this starting point, actually, we quickly, right? We quickly can tell the initial position for the loops, right? So what else we know? We know that the roots start moving from their origin, right? They start from it starts from here, so this should start from here, right? To the right side, and this starts going there, right? So these are the things that we easily can understand, right? And then in uh this region, we are seeing that this root should intersect each other, right? Somewhere. We don't know where, but there should be some collision in here, right? That two roots become at a certain point, and then they will deviate from this point out to somewhere, right? So far we know this, right? And then the next level, which is also easy to figure out, is what will happen when the k goes to infinity, right? When the k goes to infinity, if there was a zero, we know that these roots at the end will go to zero and to infinity, right? But here doesn't have any zeros, right? So we know that the trajectory of this pulse should go to some infinity place, right? And then we want to know how it goes to the infinity. So what we try to do is basically, uh, so we know the pole's supposed to go to infinity, right? When the poles are going to infinity, then it seems, let's say, I just put some, let's say the poles is here, right? It's very far from the initial plane, right? Let's say you are assuming the pole is very far, right? Once the pole is very far, what the pole is, I mean, this point is seeing from that far is basically it is seeing just whole of these poles are located at very close tiny location, right? When you are very far, you cannot distinguish these poles are separate, right? Or the zeros. So basically, once you are very far, what you are seeing from far is basically you are thinking that all of the poles are basically, you can say that in the average of the location from very far, right? So basically, you have one pole at 0, one pole at -1, and the other at -5. So the average of the location of this pole will be what? Just sum of so -5 minus -1 plus 0, right? -5 minus -1 plus 0 and divide by 3. You will see the average when you are very far will be -2, right? So from very far locations, what you are seeing basically is you are seeing some third order pole because they are three poles, right? All located something around -2, right? This is what you are seeing once you are far. And then if this is the case, then you can basically tell that, okay, I want to know what is I mean, which location this can give the negative 180-degree phase shift. So from far, assume you are having this phi uh, angle, and you have three poles. So basically the phase of this point is negative 3 times phi, right? And this negative 3 times phi should be pi plus 2k pi, right? We are looking for the phi that basically provides the negative sign. And then the phi is easily can calculate it with negative p over 3 plus 2 over 3 kp. And based on the k, it has 3 or more.
So is it not -2?
Minus 2 over 3. Where? You mean for this region? It will be 2k divided by 3 times v, right?
So
Oh yeah. It's close. It doesn't matter actually because the k you will change it can be negative or positive itself. But yeah, true. Yes, it's negative. Yep. Right. So if you put the k 0, then it will be negative pi over 3. So means one of the far poles is seeing negative pi over 3. And if you put the k over k1, then will be positive pi over 3. So the next answer is this. And then if you put the k of 3, uh, should be p, right? Is it? If I put 1 is 2 over 3 or 3. Yes, okay. If I put 1, actually is this. Is 180 degree. So basically it gives you three values for the phi. One is negative 5 over 3, the other is minus pi, and the last one is negative 2 pi over 3, if I'm going correctly, which will be equivalent to positive pi over 3, I guess. So this gives you some asymptom. What is the English name? I forgot it. Asymptotes. The name is asymptotes. In Persian, we call it mojanab. Maybe in Arabic also is meaningful. So this is what we can see when the poles are at very far, right? From very far, we are seeing that there are three asymptotes. And then we expect that the pole at the end is following these three asymptotes, right? So at least for this pole, we initially know that it is going through the correct direction. It's basically this pole supposed to follow these asymptotes until then. For these two poles here, we know that there is some intersection and then they will go out and then they may go some trajectory after here. We don't know how, right? I just draw something. But at the end, they're supposed to follow this asymptote. And this asymptote, right? So we know that at the end, this will go to the right half of the plane. So if we really increase the k, eventually this will be, we don't know what is the value for the k that this may goes to the right, but we know if you increase the k at the end, the poles will be to the right-hand side of the S-plane, right? So this is what we can just quickly find. First is the real parts. On the real parts, where is the location? And then we can find once the system goes to very far, the poles are going to go very far, how it is. Right? So basically these things are what I have done there, but in more general format. We try to find the average position of the poles and zeros. Basically what we did is this. We did this summation to find where is the centroid of the asymptotes, and then since we didn't have any zeros, we didn't have this calculation. So later on, we will see the other examples that also has the zero. And then this was what we calculate to find the phi. Here is theta, basically. Okay, we will continue this again. And this is what we have done so far, right? We figure out the centroid and the asymptotes. And then on the real plane, where is the locations of the poles? And then we estimate there is collision, and then we go on, right? So so let's say we want to know where is the location that these poles suppose go to the right hand side of the S, right? What is the specification for these poles when they are reaching here? Basically, they have zero real part, only imaginary, right? They only have the imaginary part. And then we have that kind of Routh-Hurwitz criteria, right? The Routh-Hurwitz criteria, basically, if we started with is like this, right? In fact, when a row of the Routh-Hurwitz becomes zero, means that the pose is supposed to passing through the imaginary, right? It's crossing the imaginaries. So we take that tool back to find the real the real situation that the poles are supposed passing or cutting the imaginary line, right? Then in that case, if we really want to find the accurate values, we need to. So in some of the case, we don't really want to find the value, but it is possible to find. So we try to find it then. So in order to find, we need to use the Routh-Hurwitz method, right? So we have the open loop, we try to write the closed loop, which will be this, right? And then we try to solve it. So the way we solve is, this time is 1 is here, right? 6 is here. The order is like this. 5 is here, and the k is here, right? And then we calculate the determinant, right? 6 times 5 minus k divided by 6 gives this. And then the next one is 0 because there is no other component here. And then from here, if you continue for the next level, it will be k again, right? But we know that if we want to figure out where is the intersection with the j omega axis, we need to actually make this row to become 0, right? And then from here, we can find what value of the k is actually make that situation happens, right? So if we want to get this row of 0, then the k should be here, and you find the k value from here, right? It's 30, right? If k is 30, then one whole row is 0, means that at the k of 30, the roots are passing the j omega axis, right? And then if we want to know what value of the j omega is, I mean, there are two things. There are two things. First of all, there is a k that if you put that k, then the roots will be here and here. But on the other hand, we want also know what is the value of this location of the root, right? So the first equation we reached, where is The first equation we reach from here is telling that if you put the k equal to 30, we will intercept the j omega axis, right? And then in this situation, if you remember, when we reached to this situation, we used the auxiliary equation again. And the auxiliary equation is basically the one row, top row. We use the top row to write the auxiliary equation. And since it's starting with S2, we write it back like this. We put this 6 here, and then the K we calculated already was 30 is here, right? And then we solve this. The roots of this simplified equation or auxiliary equation is actually the collision point of the S with j omega, which is correct, right? Already just gives you j omega. So this is how we use the root service technique to figure out the intersection of the poles with the j omega axis, right? And then we need to find some more specific things. I will just go through the example. So we want to actually find the, let's go, let me summarize this so far. We have the root here, one root here, and one root here, right? We know that this area is the root location, and here was one negative 5. We know that some centroid or asymptote is at -2, and they suppose having like this, right? So far. Next level, what we calculate before with the root service is how this pole is supposed to pass the j omega region. We know at the k of 30, it will reach to this j omega, and then this value was j root square of 2, if correct, right? Root square of 5. Yeah, so far we know this, right? And then the other thing we want to find is where is this location, the collision point of the two roots. To calculate that collision point, basically this is the two roots are at the same position. So in order to do that, so you first again write the closed loop equation, and then you rearrange the closed loop just based on the k equals to something, right? And then you take a derivative of k respective to s. So basically what it remains is doesn't have any k, right? It's just a derivation of this kind of polynomial, right? And it gives you several uh, roots, right? But not all of them are acceptable. Maybe you should check whether these roots are inside inside the acceptable root location on the axis or not, right? So the two roots are, one is negative 0.47, the other is negative 3 point something, right? So we know that from -1 to -5, there is no place for the root, right? So this one is not acceptable, but the other one is acceptable, which is showing where these two roots are supposed to collide each other. So is something near the middle of the two roots, but not exactly middle, is -0.47 something. So it means that this location of the -0.7, and then now we know this guy is going up and then passing through that specific k of 30 and colliding this j omega of square root of 5, and then go to the asymptotes. So basically here is the thing, right? We call this breakaway or break-in point. Right. These are what we need to find at the end. This is the trajectory of the poles when we are sweeping the k from very zero to something infinity, right? And then from this, we can know how the system, the closed loop system will react, in fact. So we see if the k is too low, then the system open loop basically is semi-stable because there is a root at the zero. But if you increase the k, the roots start moving to the left, right? And then maybe still the speed is not too good from this response because two real pole, one is next to origin yet is slow, right? We don't like the root to be very close to the origin because it becomes more slow to damp the response, right? And then you keep pushing, increasing the k to push the root back more from the origin, right? Eventually you reach this collision point, which is kind of critically damped, but at the same time, this third pole is just going to the infinity, right? So the third pole in this case for us maybe is not the concern because already it's far. So the response of the third pole is not going to limit us in uh, in the final time domain speed performance, right? Because this is already very larger than the other ones. So our response is limited to the poles near to the origin, most likely. And then you try to increase furthermore of the k, you see that the poles become imaginary type, right? And then it looks like the imaginary uh, second order system at a certain point. If you ignore that the third pole still is far, you can actually ignore it. So, and then like a second order response, you can adjust it to get reasonable overshoot or damping factor, all of that things. And also, if you increase the K too much, like 30 above, then the system will be unstable, right? So let's do some modification on this open loop and see how it will work, right? So, so here, this is what we had initially. This is what we have initially. Let's say we can add like a zero to the right-hand side, to the left-hand side at s equal to -1. Let's say you design one controller so that you add this zero at -1. What will happen? So can you describe, some of you, what will happen to this when we add extra zero to this? We put 1 0 where just on top of this pole, right? Then what will happen if we put the poles on the zero? Yeah, they will cancel each other, right? From the open loop, you can easily can tell that this will cancel this, right? But even if you don't consider that, you can assume that the two poles are the pole and zeros on top of each other, right? So again, you can do the same way to figure out where is the root location. So this region is root location because the right side is only one, the odd number. And also this region is the root location, right? Because there is a three of them, right? It's 1 0, one pole, and two poles, basically is. So whole location can be basically the root location, right? And then this region afterward cannot be the root locations, right? Because now you have four of the I mean even number of the root and poles. Basically what you have is like you have only this region of the root on the real, right? And first of all, even if you do not continue, we will see that this already is a stable, cannot go to the right half side, right? But you need to find where the location of the collision is and that kind of things again, based on the root airways or any other ways we already described, right? And then what is here is drawing basically is once you put it there, in fact, the root locus will build something like this, right? Right, so it seems that putting the left hand side 0 make the system more stable. Just a quick conclusion. So what if we put a right hand side 0? So this is the initial system we had. We are trying to add 1 0 at where? At, let's say, 2. What is happening? Can you try to plot the location of the poles in this situation for the real part first on the real axis? You can try. Right, basically, let's do it that way. Basically, what we have is this, right? We have 1 0 pole at 0, 1 pole at -1, and 1 pole at -5, right? We are going to, is -2, I guess. We are going to add 1 0 right hand side 0 at 2, right? So what is happening? What is happening? Oops. Where is it?
Shifting the average,
Shifting?
like changing the value of the average.
Yeah, the value of average changes, of course. But before that, what is the problem on the real part? So 0, -2, -5, and let's say 1 0 at 2. Where is the root locus on the real part? Can you tell me? This is 2. This is 2. This is 2. Yeah.
-2 to -5.
Sorry.
From -2 to -5.
Yeah. Is it the root location or not?
Yeah.
You mean from here to here? This region? Why? How many poles are at the right side? 3, right? It's correct. So then here is one location for the roots. How about the from -2 to 0? Is there any root location? Right? And how about from 0 to 2, +2? I mean, I'm talking about this region. Is there possible to have the root location to be here? It is possible, right? Because you from here you actually have one pole or 0 at the right. So basically you have odd number of poles or 0. Right? Then you are here the right side of U, actually you have odd number of poles or zero. You have 1, 0. So it's odd. So basically this region can be. But if you put yourself here, you are seeing even number of poles and zeros. So you are seeing 1 pole plus 1 0 is 2. So this region cannot. And then again, once you are here, you have 3 poles and 2 poles plus 1 0. So basically 3 and then odd number, then this is possible. And how about after -5? After -5 also is not the root locations, right? So what is the problem with this so far? What is the problem with this root location? Do you see any problem? Yes,
Unstable.
that's true. So it means once you are start increasing the k, right, this pole starts moving to go to this 0, right? From very beginning, it's just unstable from very beginning. So in fact, if you have this right side 0, then you cannot stabilize the system, right? You can easily find this, even don't need to go to the next level of equations or, right? So what is here showing is basically that this pole starts moving to the right side of the 0, right? But if you follow up for the other things, you will figure out there is some asymptotes and some centroids, and then the other 2 poles will collide somewhere, and then they separate, and then they go to some asymptotes, right? So next level here, we are adding one more pole at -2. What will happen? So we had this -1, we are adding this -2, right? So again, we go back to the real part, see where are the location for the poles at the real part, right? So we know that this region is the location for the pole because the right side is odd number, right? From -1 to -2, is there any root location, right? Because the even number of poles. And then from -2 to -5, again, since the odd number, there is a right a location for the poles. And then what we are seeing quickly from here, actually, we figure out there should be 2 collision points between the 2 poles, right? And how about the centroid value? How to calculate the centroid value? Because I'm going to, let's say, find the asymptotes. So for the centroid value, we need to add all of the poles. We want to basically know when you are very far, when these roots are basically are concentrated, basically, when you are looking at very far region, right? What you are seeing is 1, 0. You are seeing the average of the basically poles and zeros. So you have 1 pole at 0 plus -1 pole at -1, 1 pole at -2, and 1 pole at -5, right? You sum it and divide by 4 is the location of average of these poles, right? Is what? -8, 2, right? -2, correct? So basically, when you are seeing everything very far, you are thinking that all of the poles are at -4. -2, right? And then from the other equation, you can find how many, let's say, theta or phi of this kind of asymptote. So I just take that formula of just it should be something like negative pi over 4 plus some rotation 2kp over 4. So I'm just driving based on. So if the k is 0, basically is negative pi over 4. Negative pi over 4 is like this. Is like this. This is negative pi over 4. The next one would be like this. The third one should be like this. Last one should be like this, right? Actually, this asymptote and the way it goes, it already gives you whether when the k is going to infinity, where the pole is supposed to go, right? It shows that you see that there is two asymptotes like this and this, where it means that some of the poles has to go to the right hand side of the S-plane, right? So basically, this already tell you this will eventually will be uh, unstable if you increase the k too much. And once you have more number of poles, basically, you will have more number of these asymptotes at the end. So for the second, let's say for a second order system, when you have only two poles, these asymptotes are only two lines. It really depends on the number of poles and zeros. So when you have a second order system, you will have only two asymptotes at the end, which will be something like this. I just usually is like this, is starting at some place, and one is on the real part, the other one is an imaginary part. So most probably if the real part is okay, then the imaginary is not supposed to go to the right side. It's just vertical. So it means that for the second order system, usually should not be unstable when the k go high. But from, let's say if you have third order, right? When you have the third order, then these asymptotes, you will have three of them. And once you have three of them, is something like this, something like this, something like this, right? And then these two are saying that if you increase the k, it will be unstable at the end. And now you are seeing if we have four, basically like this, then again, we have some asymptote that's going to the right side. And if you have more, actually, it becomes even worse. You will have, let's say, more than of these asymptotes lines, right? Most of them go to the right side. So that's why we are saying when the system, we add more poles, the system has more chance to become unstable. Okay. So here is some more examples that we just quickly try to catch it. We don't need to go through the details. So basically what we have here is this system has one pole at -5, and one zero at -5, maybe I put it here, -5. And there should be two poles. Where is the other pole? Is it showing here? Not yet. What are the poles of this? Do you know? What is the pole of the open loop? S plus 4 square, right? Basically, the two poles are at the third one location at -4, and we have 1, 0 at the right side. So can you tell me where is the location for the for the roots on the real axis. On the real axis, which location can be the root location? Can it be -4 to -5? How many poles or zeros we have on the right hand side? Basically, is 2, right? This root is second order root, right? I put two roots on together, so basically it's second, right? Is even. So here is not a root locus then, right? How about larger than -4, between -4 like to 0? Cannot, right? And how about less than -5? Can, right? Is 3 whole and zeros, right? So here can. And what else we know? When the k is 0, what is happening? The root location is where? We try to find the trajectory of the roots, right? Start from this k of 0. When k is 0, the roots are where? Hmm? Any idea? No, when we are starting with the k of 0 means the system is coming is like an open loop, right? Because you remember the system? The system, you have the g and you have a k factor here, and the loop is closing, right? When the k is 0 here, means you are not doing the closed loop basically. So the poles of the system is basically the open loop. And the open loop is just the G or GH. H is once we have the H here, right? It remains at the this location, right? -4 when the K is 0, right? Okay. So now we are seeing that we expect the poles are starting from here and going somewhere, right? But we know it's not supposed to go into the real part, because the real part between -4 to 5 is kind of not the location for the closed loop roots, right? It's not same as before this time, right? So then this time we need to know how these poles are supposed going out, right? So let me just focus more again back here. You have -4, 2 poles here, and 1, 0 here. So we don't know where the pole is starting going out. We just assume that somewhere on this circle is going out, small circle around it. And then we don't know what is the phi or the theta of the outgoing path. We just assume it like a known variable, right? And then we try to calculate the overall phase for uh, this node, this point that we are assuming the poles suppose going out. So at this point, for this point, the phase that we are seeing basically is -2 times of phi by -2, each, because there is 2 poles. Each poles provides negative phi, and the 2 poles are suppose 2 times of it. And then from here to the 0, the phase of this point respective to the 0 basically is almost 0, because this circle we are assuming is very tiny. So it's not making that big angle with the 0. So basically it's assuming 0. And then -2 times of 5 2 times of phi plus 0 should be what? Should be pi plus any multiplication of the 2 copy, right? So the purpose is to reach to the phase of -1. And this gives us the phi has to be negative pi over 2 plus kp. So means that, let's say the k is 0, then the phi is negative pi over 2, and then for the larger k, it will be negative 3 over 2, or is like plus pi over 2. Basically, this way you can figure out how the pole is supposing running away. It says that the the trajectory of the pole to exit is 1 plus pi over 2 and the other one negative pi over 2, right? Right. And then what else you can figure out from this? We know that the po we know that the okay, we can find the centroid again afterward, right? The centroid is where we have two poles at -4 plus -4, and one zeros at -5, right? For the zeros, we do another -5, and then divide by 3, because overall, oh, sorry, divide by 1. When you are looking from far, it looks like there is just one pole. One of the zero is kind of canceling the pole, so it remains only a single pole when you are looking at very far, right? When you are looking at very far to this system, right? But you are seeing that one of these pole and zero may cancel from very far, and it remains only a single pole. And then the average of this single pole is somewhere like here, basically. Will be -8 plus 5, -3. Is it? Yes. Yep. It's kind of -3, what you are seeing. And since at the far you are seeing only single pole, then the asymptote is only on the real part. So we don't need to actually draw it, basically. So what we know so far is there is two poles here. The left-hand side is nothing, but we know the pole will exit with these angles, right? 90 degree, -90 degree. And then what we'll expect to happen is this pole's supposed to go to the zero at the end, right? So they should go back somewhere to this zero. In more general cases like this, it comes to collide somewhere here, which is the thing, and then the split to zero and then to the asymptote. Right, this is one general case that can happen. Do you think there is any other way that this may split and combine and collide? Do you have any idea if possible to? Is it possible that this pole separate from here? Let's plot it with different color. Is it possible that this pose comes out of here, right? And somehow collide over here, right on the zero? Do you think so? It's not possible this to happen. right? If this happens, means everything just cancel off each other at certain point. So the most common thing may happen is just coming back to this center node here somewhere and then split it to 0 and the other one goes to infinity. So let's try to see the other cases like this. These are some examples, or just to see different cases, right? So first of all, what we did is try to find the pole and zeros of the open loop, right? So the 0 is clear, is -1, but if you maybe simplify this, you will figure out there is one pole here at this -4, right? And it will be some second order equation that has a complex poles. One is at what negative uh, oh, is at the origin, right? Okay, it's easier then. Yes, this is at the imaginary part. So basically it will be like S2 plus 4, right? If you try to simplify this equation, you should reach to this because it gives you two complex pole with no real part, right? These terms, this term, right? And then one pole at -4. So again, we go back from the real part, right? Starting from real, see where is the location possible. Here can possible to have it. This is only real part that we can. And then what else? How to decide for the other things? We should figure out how the poles are exiting from these locations. For this one is clear because it goes just to the 0. For the other, again, you need to draw some unknown field of the exit from this pole and then try to calculate the phase of that imaginary point respective to the other things, right? So let's say from this pole, then nearby pole, the phase is negative phi. From this point, from this pole is kind of 90-degree, right? -5/2. From this point to this 0 is how you need to calculate this angle of this triangle, right? It might be positive pi/3. Why positive? Because I am measuring from a 0. For the 0, the phase are positive. From the poles are negative. And from this point to here is another triangular thing. Is how it should be -pi/6. And if you do the calculation, you will come up that the angle will be something that comes out at this direction, right? It's not going to the right side. Shows that this will be eventually stable, not going to the right side. So, okay, I guess this thing needs to do more practice and takes more time to do so. But I just want to quickly review what we can get very quickly. We don't need usually to solve all the details. So again, this one, let's say the poles and zeros location are like this, right? quick things is we know the real is here, the real is here, right? Once we have here, we know that this thing should collide and go out like this. And since the order of the system is basically 1, 2, 3, 4, right? Four poles, 4 poles and 1, 0. When you are seeing at very far to find the asymptotes, it would be at the end 4 minus 1, like a 3 pole when you are very far, right? And when you are very far, the 3 pole will have 3 asymptotes, like from some centroid to somewhere. And then we expect some of the poles should go to the right-hand side, right? From this general knowledge, then you can just estimate how this can be, even without accurately solving. Yeah, okay. So this was the root locus. There is another technique we need to know, which will be at the end more useful for the circuit designs usually, which is the based on the basically frequency response instead of using the S. So in circuits, we usually work with the sinusoidal inputs. And once we go to sinusoidal input, then what we are really more care about is the basically the Fourier. But the Fourier is the special case of the Laplace transform, right? Once you just assume that the S is just j omega, it's not it doesn't have any real, right? Once you have the system with g of S, let's say, right? This is the first order. So once you apply a sinusoidal input, what will happen? As you saw in the study, the phasor in the circuits, right? Once you have the basically sinusoidal input, you can just focus on the, let's say, final steady state values, right? And then you just put the S with j omega because we are just caring about the sinusoidal input, and then we are just caring about the steady state, right? In that case, what you will have is basically j omega tau, let's say for this first order, plus 1. And this will actually modify the amplitude of the input and the phase of the input to the output, right? Then the g of j omega basically has some amplitude and some phase, right? The phase of the g actually will add to the phase of the input, and then the amplitude is just multiplied by the amplitude of the input, right? So in this case, let's say for the first order, the amplitude of the g, or the magnitude of the g, basically is this. If you simplify this complex function and try to find the absolute or the magnitude value, it will be like this. And usually, in order to plot this amplitude and the phase, we use the logarithmic scale, which we call this logarithmic scale and plot as a bot plot, the bot plot, right? So why we use the logarithmic scale? Actually, it make it a little bit more simple when you use the logarithmic scales. It make the curviest thing to more like a straight line. If you want to really plot this function over omega, right? This is like a curvy function, like a square root, and right? But once you go to the logarithmic domain, you can make some rules that make it more like can estimate it with a very straight line, or the demonstration is easier, right? And then on the other hand, we need to care about the phase of the G, and the phase of the G is just to calculate the phase of this function, the complex function, right? This is a complex value. The K has no phase, positive number. The denominator has a complex number, and then the phase of this denominator basically is the tangent inverse of the omega tau. And since in denominator there is a negative sign, basically this is how we find it, right? And then there is a rule to plot this. So let me clean the bit. So we try to plot on the logarithmic scale, right? The logarithmic frequency, and also for the amplitude, we use the 20 log of the magnitude. It helps us to easily manipulate, or for example, when we change the K, it means we are basically shifting this curve upward or downward, just easily by adding, since it's a log scale. Otherwise, you need to just do the multiplication. So this is a better way. So let me see if okay. So we go several extreme cases. So what will happen when omega is very low, like 0 in this? When omega is very close to 0, what will remain is basically we are seeing that 20 log of k, right? So the initial point is basically 20 log of k, right? When the omega is too low. And when omega is basically at the position of the pole, means omega is 1 over tau. What will happen is always for the first order, this value will be negative 3 dB. I mean k minus 3. 3 is just because 20 log of, because if you put the omega of 1 over tau in here, you will have like this, square root of 2. And 20 log of this will be negative 3. So when we plot the amplitude, basically, here we have the omega. There is some pole somewhere at omega 1 or omega 0. At very low frequency, we are assuming that this thing is constant, and the value is, depending on this k, is 20 log of k. But once we're reaching to that pole region, right, it basically drops 3 dB. But for the simple plot, we do not even show that. We just assume that it's just fixed. And after that, what will happen once the omega is too big? In this equation, if the omega is too big, then you can actually ignore the 1, right? And if you ignore the 1, then it will be simple. It will be 20 log of k divided by just omega tau, right? And this simple thing is saying that for actually it shows it has some slope. You can say that in the log scale it only has some slope. It's like a straight line dropping, and the slope of this line, let's say I just plot it over here, is negative 20 dB per decade. Per decade means once you are, let's say here, at certain omega, let's say omega 1, if you increase the omega 1 10 times, 1 decade, then the amplitude will drop by 20 dB more. This is the way we describe it. So if I go 10 times of omega 1, this drop of the amplitude is 20 dB. That's why we say that for the single order system or circuit, the amplitude at the high frequencies is dropping by negative 20 dB per decade. So how about the phase? The phase, we have this equation for it. At very low frequency, there is no phase. Tangent inverse of almost 0 is 0. At very high extreme, when the omega tau is going to infinity, what is the tangent inverse of infinity? Pi over 2. And since it's a pole, is negative pi over 2. So starting from 0, right, the phase, and then go to negative 90 degree or pi over 2. And what will happen at exactly at the pole location? The pole location is 1 over tau here, right? The pole location is omega 1 over tau. At that location, tangent inverse of 1, right? Omega tau is 1, is negative 45 degree. So we know that always at the pole location, the phase is negative uh, pi over 4. Okay, and then we can continue this for second order. We usually do the things for second order and first order first. For the second order is a bit more complex, but some of the things is still valid from the first order. First of all, let's say the amplitude at low frequencies, when omega is very close to 0, you can just easily put 0 there and figure out what it is. It's like the K or something. Depends if you have K, or if in this case is 1, 20 log of 1 is 0. This is the dB 20 log is 0. 0 means 1, right? And then once you reach to the poles locations, right? There is a pole location. Actually, in fact, in here, since it's the second order, we usually uh, deal with the omega n, right? If you remember, we usually deal with omega n over there. In here also, we try to show actually a scale based on the omega n. So here we define this ratio. So once we reach to the frequency next to omega n, depends on that delta and which showing the overshoot or overdam and other things. We actually have this kind of curvature at the omega n, close to omega n, right? So in the case of the, let's say, critically dam, over dam, or under dam, all of the case actually equivalent to this. So for the lossless, basically, if you remember, for the lossless, in fact, this should have a very large peaking, means at that special frequency, this should have is kind of having too much gain at the special resonance frequency if it's lossless, right? Which we don't like it. So this peaking over here in the response showing basically how much system is, which side. Is it overdamped? If it's overdamped, there is not peaking like this. Like is if critically damped, one of them, and then like that. But what other thing is important is once the frequency is going to higher than this region, we consider the several extremes. Omega next to 0, omega is infinity, and omega at the region of the pole, right? At the region of the pole is like this for the second order, but at infinity is how? At infinity, since basically you can tell at the infinity your pole will be, you don't care about the these terms because they are lower order, right? But this is like second order. So at infinity, this term will be dominant. Basically, the system will act like s square or j omega square, right? And then if you take the 20 log of this to find the amplitude, what you will have is basically similar to here. Here was dropping 20 dB per decade, but since this is second order, the drop is sharper, is 2 times, 40 dB per decade. And how about the phase? So the phase is almost similar to the other case. Basically, this is a second order pole. So at the very low frequency, you can see that there is no phase shift. At the very high frequency, also, as I mentioned again here, at the very high frequency, you can just assume that the system is just j omega square, right? I just ignored the first order and zero order terms when j omega is high. And this will be negative something, right? Negative omega 2. The phase is actually 180 degree, right? So start from 0, go to 180 degree. And at the middle, at the omega n range, is passing around 90 degree. This is for the second order system. Uh, but we need to know how we are going to use this as the criteria for the stability, basically. First of all, we need to know how to plot this, right? To plot, we go from the low frequency and then try to estimate how the behavior is at the higher frequencies, and then how is the behavior at the region of the pole, both amplitude and phase. And then how we can use this for the finding the stability problem in our case. Basically, we want this to understand the stability. So, what we need, in fact, if you remember again from the previous thing, is that we want to actually find where this 1 plus k times g, which is the roots of the closed loop system, is 0. Right? Again, going back to the initial thing. And then we go that kg is -1, right? If this situation happens at certain frequency, means that there is uh, because now we are exciting with the sinusoidal. So if this equation happen at certain frequency, means that that frequency basically is the pole of the system. And since imaginary, it tends to be unstable because it's right at the imaginary part, right? So we should figure out from this both diagram, basically, when this situation is happening. The amplitude of the k times g should be 1, but the phase should be -1, negative 180 degree, basically. Okay, let's do some examples first for simple things of the both plots. So let's say if the system is only single zero, the way we plot the both, basically, the both diagram is we assume that here, can we assume that the S is omega, if we put it Sj omega and omega is 0, what will happen to the log scale? For the log scale, if we put 0, it becomes infinity. So we not just starting at 0, maybe slightly more to be able to show it. But if S is 1, I mean j omega is 1, then it will be 0 dB, right? And then since it is just a like single zero, this slope basically is positive 20 dB per decay. What we want to know is how this slope is. And since there is no pole at 0, it doesn't have anything, just with this slope is going up. And for the phase, since only single pole at the single zero at the center or at the origin, the phase of j omega is always 90 degree, positive 90 degree, right? So how about this 0, not at the origin? So now we can actually start from omega of 0. We can put the omega of 0 over here. There is no problem for this case. So as low omega is kind of 1, right? If you put j omegas and omega is 0 is around 1, so the 20 log is 0. And just we assume it's constant, right? Up to the 0 or pole. Now is 0. The value of the 0 is omega is 1 over tau. At this region, we are starting just breaking, assuming that after this, it behaves like the infinity. And since this is a 0, we start increasing with 20 dB per decay, right? We just simplified it. In fact, it's like this, and here it is actually with some curvatures goes to high, but we just simplify it for our case. And how about for the phase? The phase will start with a low frequency, which is 0, right? And at the high frequency, it will be 90 degree. And this transition actually, in fact, we are not going this sharp for the demonstrating of the phase. We basically try to make it something like this. We assume that it is happening, a start phase shift happening like 1 point, I mean, before 1.1 times tau and continues up to 10 times over 5. We just break it, spread it. It's not just happening so sharp. So again, this is showing the bot plot for another single pole again, right? At this pole, as you are seeing, it is just first plotting these asymptote lines. And then we even do not need to show this negative 3 dB point, which is at the pole, but we need to know this how far, which slope this is dropping. And the phase for the single pole, as we mentioned, starting from 0, going to 90 degree. In the middle of the pole is negative 45, right? So the way initially we go is like we go like this, sharp, but we are bit make it more accurate, starting from 1/10 of the pole to 10 times the pole, like this. And then more practical thing is coming up when we have multiple poles and zeros. So now here we have 2 poles, right? One pole is at omega of 1, the other pole is at omega of 100. So again, we try to plot it. Let's see. When omega is very close to 0, what is happening in this function? What will happen when the omega is very close to 0? What the whole g of gh is what? When omega is very close to 0, right? You just put this s equal to 0, right? Is what? Is 1. And then 20 log of 1 is 0, right? The log of 1 is 0. So starting from 0. And then again, we are assuming everything is constant, right? Until the pole, the first pole. It's just simplification. And then after reaching the first pole, the magnitude start dropping with the slope, right? The slope of the first pole. Basically, we have two poles, right? One is belonging to S plus 1, the other one is for the S over 100. So when we are reaching to the first pole, actually we are still far from the second pole. So from the second pole perspective is not still effective, basically. Right, so it's still like a first order system so far, and then the slope of drop is like 20 dB per decade until we reach to the second pole. When we reach to the second pole, basically the effect of the second pole is also coming in. And it also add another amplitude drop, another 20 dB per decade. Or the second pole will be added to the first 20 dB per decade. And then the amplitude drops sharper, right? So this is what we need to plot first. From the phase perspective, what is happening? Again, at the very low frequency, the phase is 0. We are seeing the first pole at the beginning. At the pole itself will be negative 45 degree, right? But since we are far from the other pole, this doesn't have any effect yet. And then if we just assume that we had this single pole, it should eventually go to the negative 90 degree, right? But we are reaching close to the next level of the pole, right? And that pole also added some phase by itself from whatever it is. It start adding 90 degree more phase shift. And eventually what we are seeing can reach to negative 180 degree, right? This is obvious, right? At the high frequency, it can reach to 180 degree. Why? Because at high frequency, actually, you may simplify this with just S2, second order. You just ignore the other terms, right? Lower order terms, since the frequency is high. This term should be dominant. And then if you put j omega, it will be negative omega 2. So it goes to 180 degree, right? But in this transition, sometimes is important for us. So in fact, what we want is, if this situation happens, the system will be unstable. This situation is when will happen once the magnitude is 1 and the phase is exactly 180 degree, right? When this equation will be 0 is the magnitude of g of h is 1, but the phase is negative 1, basically, or 180 degrees, so that this will be 0, right? And this means that the system becomes unstable, right? Then basically we go back here, for example, right? We check if these two conditions are simultaneously happening or not. So for this example, is this happening? So when the gain is 1 or 0 dB, when is the gain is 1, how is the phase? Phase is 0, right? So it's too far from 180 degree, actually, right? When the gain is 1, the phase is 0, and we usually compare how far this phase is from 180 degree, which is the start of becoming oscillatory, right? And we called it phase margin, phase margin. So for this case, the phase margin is what? The phase margin is 0 minus 180 degree. We always compare with 180 degree. Means that it has 180 degree of phase margin to become unstable, right? On the other hand, we also go back to, let's say, high frequencies or the frequency that the phase is 180 degree, but we check for the gain, right? There is other way also. So we go here the phase is 180 degree, but how about the gain? The gain is pretty low, right? Negative 40 dB is 0.00 something, right? Is too low, is too. So if the gain was one, then this could be resulted into this equation to become unstable, right? But since the gain is low, so what is this situation we are talking about? We want to solve this equation, but now the amplitude is something very small, let's say 0.001, but the phase is negative, right? Phase is negative means that uh, phase is negative. Oops, where is it? Yeah, phase means negative is is not going to pen. Is like this, right? G of h, the magnitude is small, phase is 180 degree, but cannot be zero. I mean, this equation cannot be zero. It's not at the oscillation region again. So we are comparing this value of the amplitude to what? To 1, to find the gain margin. We say how much margin we have to, from the gain perspective, to reach to the oscillator region. So then we define two criteria. One is the phase margin. We go to the amplitude of 1 and see whether the phase is next, how close the phase is to the 180 degree. Or on the other case, we go to the phase of 180 degree and then try to see whether the amplitude is close to 1 or not. If close to 1, then means it's possible to become unstable. Right? So here is just demonstrating some cases. Let's say you had plotted the board for a system, this system, right? Then you want to check whether the system is stable or not, right? So you go to the frequency where the amplitude is 1, right here, or 0 dB, and then check the phase, right? You will see from this both diagram that the phase is something not reached to 100 degree yet, right? And then the distance of this phase to 180 degree basically it says how much stable your system is. And this you call it phase margin or positive phase margin, means that it still has more room to reach to 180 degree. So this system, let's say we call it stable, right? In the other case is how the other unstable case is this. So again, you try to find where the amplitude is 1 or 0 dB, right? And then that frequency, you check the phase, right? You see the phase already passed 180 degree, right? It means that it is very possible that this system become unstable because the phase already passed 180 degrees. So there should be some point in, in between region that is passing that criteria of the oscillation happens. So here we say that there is negative phase margin. So this system can be unstable, but this system is stable because still phase has not reached to 180 degree. Okay. So I want a bit describe more for this more intuitively rather than this. We still have some time. So basically what we are saying here is this. You have a system, right, in a feedback. Yes, your system, you expect to be a negative feedback, right? The negative feedback is the good feedback for our controlling, right? The negative feedback we show usually is we are showing with this sum and negative sign here, right? We are applying the negative of the output to the input, right? To be a negative feedback. But once if you check in a different frequency domain, in a different frequencies, let's say for the low frequency, the system is like a constant amplitude and zero phase. Usually it's like this, right? When you plot the both diagram, right? The phase usually start from 0 degree and then dropping, right? So for low frequency, basically it's like the constant gain and no phase. And then when no phase, then you have this negative phase, I mean the negative sign here, and the feedback is still is negative, right? But what will happen when the frequency goes up? When the frequency goes up, actually, the amplitude may change, right? Because you have some poles, some zeros, the amplitude will change. But on the other hand, this G or G of S or G of J omega, right, had some phase for higher frequency, right? What will happen if the phase actually reach to something close to 180 degree at certain frequency? What will happen? Yes, because this G of J omega, it induces 180-degree phase shift by itself. And then in you're closing the loop, actually you have another negative sign always initially, right? And this too becomes a positive at the end, right? In fact, for that special frequency, this loop becomes a positive feedback, right? When you have a positive feedback on the certain frequency, then it may have chance to oscillate at that frequency. And actually, this is the way that the people build the oscillators. So the oscillator circuit, they actually make this condition happens at certain frequency. At certain frequency, the feedback loop becomes a positive feedback. So it will keep increasing the itself instead of confining the output. Excite itself until it reach to the saturation and keep oscillating, right? So this bot diagram actually is trying to show us how far actually the phase is when the gain of the system is 1 or 0 dB, right? So you always remember this, right? We want if this happens, then the system is supposed becoming unstable. When the amplitude of the system is 1 and then the phase is 180 degree. If it's not still reaching to 180 degree, it's okay. We are saying that this is still stable. Okay. But what will happen when we go higher frequency? Like, at the end, it may reach to 180 degree, right? What will happen? Why is not unstable? Do you have any idea? I mean, though we are saying this is stable, right? This is stable. But this also, after certain frequency, the output phase can be 180 degree.
Again, in the positive side,
In terms of the
increase.
In terms of the sign, it will be positive, really, right? Because this at the end, the phase will be more than 180 or 180, right? But why this case is not making stability issue? You have an idea? The reason is once the phase is reaching 180 degree, right? The amplitude is too low, lower than 1, right? No, the amplitude is always a positive number. In logarithmic scale, yes, negative. But this is the logarithmic that's saying below 0 means the amplitude is less than 1, right? So this case is what? This case is saying the feedback is kind of positive in terms of the sign, right? But the gain of the system is not high, is less than 1. Since the gain of the system is less than 1, it cannot boost the like inside the loop, it cannot boost anything to rise. It cannot grow the signal internally because there is no gain for that, right? The sign is positive, but there is no gain for that to build up. So for this one, the problem is this, the unstable system. Actually, the unstable system, when the phase reaches 180 degree, the system still has some gain. It means you have closed the loop with the feedback, positive feedback, and you still have some gain. And this gain actually has potential to build up some oscillation. With no gain, you cannot build the oscillation. Intuitively, you can tell this. Let's say you have the system has a gain of, let's say, 3, right? And then it becomes like a positive feedback. What will happen if you have some small signal like 0.1 or something, or let's say start with 1 at the input, something happens that this one happens at the input. Then the output will be 3, right? And this 3 will come back to the input of the system, will be 3. 3 times 3 is going up, right? It will not down. That's why if you have a positive sign feedback and the gain is there, this will grow up. But what if you have like 0.1 inter gain, right? If the gain was lower than 1. If the gain was lower than 1, if you had something like 1 volt at here, then the output becomes 0.1, right? And then it is goes back to here, 0.1, multiply dropping, right? It will not grow up, right? Though the sign is positive, the sign of the feedback is positive, right? But since the gain is lower than 1, this cannot grow up. It's not only the matter of the sign, also the gain, right? So that's why we check like this. First, we see this location where the gain is 1. We want to know whether once the gain is still 1, if the phase is correct or not. If the phase is less than 180 degree, that means there is no chance for the sign of the feedback to become positive, though you have gain. And then the other case is saying, the other case actually is saying that once you are reaching 180 degree, right, you still have some positive gain, some more than one gain, then this system can be kind of becoming a positive feedback over that frequency, become unstable. So we stop control uh, system course up to here, basically. And we will give you some assignment to practice. We will have some solving assignment sessions, and this should be enough for our next level of study for the circuit stability and So basically, you need to a little bit work with these three types of techniques to find the stability of the systems. Root service, which based on the polynomial, root locus, which try to estimate where the roots are moving. And then this both diagram is a bit more useful for our circuit design because we are actually trying to understand where the system sign is changing and becoming like negative feedback becomes a positive. You can think like that. Yes, so I know I talked too much for this course, but we had limited time. So
it's like a little bit new, that's why.
yes, it's a bit difficult to give this examples and it's not that straightforward, but you need to do some practice. So from tomorrow we go to electronic circuits. So over there is more interactive, can be more interactive, and we can do some more showing some more simulation things or yes. But these are a little bit fundamental and we will use it later some ways, not exactly like this, but the both will be used more for us. Any questions or anything from this course or any course or anything? Sure.
If it's coming the Sunday first, or is it only signal processing?
The exam, you mean the next exam? The next exam is only signal, I think, yes.
Not included in the.
No. Yes.
So is it like signals and control or only?
I need to check with Dr. Hassan. Don't know the plan is how. Did he mention some? Oh, he's supposed to combine. If combine, then signal and the control together. Yeah, because are related most of the things. At least the Laplace and can combine. Maybe. I talked to him and will inform you.
The exam will be on Sunday.
Sunday. Yes. 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 From tomorrow, I start to go for the electronic circuits. So it will be more fun and easier to follow up. Yeah, electronic is better than pure mathematical things. Okay. So anything else? Okay. So yes. Then see you tomorrow. And the time is okay, right? This time is fine, I guess. Yes. See you on tomorrow. Thank you very much for attending.